welcome back. We are discussing the biosynthesis of cholesterol, and what we have found that we went up to the C5 unit stage, that how the C5 units are formed. The C5 units are basically two tautomeric forms. One is dimethyl gamma gamma dimethyl allyl pyrophosphate and another is isopentenyl pyrophosphate. We have also identified what is called the tail group and what is called the head group. Now, the way it is written now, this is the allyl pyrophosphate, this is the isopentenyl pyrophosphate. So, basically the head group of this diallyl pyrophosphate is facing the tail portion of this isopentenyl pyrophosphate. Now, this will be a very good leaving group because it is an allyl system. You know, allyl systems are very good leaving groups because of the for SN1 reaction it will be very good because the cation is positive charge. Even for SN2 also it is very good because these p orbitals stabilize the developing orbitals with the nucleophile and the carbon. That is well known in organic chemistry. Okay. So, that is very reactive carbon. So, what will happen now, that a hydrogen from here will activate this carbon. So, this is that same, this is the mechanism of tautomerism also, that the hydrogen is lost. If it comes here, you get the gamma gamma dimethyl allyl pyrophosphate. But rather than doing that, it also activates this carbon towards having a negative charge. So, that means it is a potential nucleophile. So, that now attacks the head carbon of this and kicks out the pyrophosphate. Okay. So, I write it here. So, you have a gamma gamma dimethyl allyl pyrophosphate and you have this isopentenyl, sorry, this is not iso, this is again gamma gamma dimethyl. So, the double bond is not there, the double bond is here and then you have OPP. So, now this hydrogen is lost, that comes here, attacks this carbon, kicks out the pyrophosphate. Okay. So, this is basically what? A head tail combination, head tail combination. Okay. This is the head, this is the tail. So, now the product that you will get is just a second, the product that you will get is this, then there is a CH2, this carbon, okay. Then what? Then another carbon CH2, this is also CH2, then you have a methyl, this is the first CH2, this one, this is the second CH2, that means this one, and then you have a methyl and then you have a double bond and then you have this is CH2 and then OPP. Okay. Try to count the carbons, that will be better. This is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 4, 5, 1, 2, 3, 4, 5. So, it has to be C10. Is it C10? Then you are correct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So, that is correct. So, this is the structure. This is what is called geranyl pyrophosphate. This is the first monoterpene that is formed. Now, this is, by the way, is called isoprene unit also, because the rubber that see all these things came from degradation of rubber, because rubber was known for a long time, and that rubber, if you degrade, ultimately you see that you will get isoprene, and isoprene is the hydrocarbon of this. Okay. So, these are what are called isoprene units. Isoprene units are combining. So, it is said that it is a condensation of means basically two isoprenes. Okay. Two isoprene units, these C5 units are called isoprene units, but to be precise, one is this gamma gamma dimethyl allyl pyrophosphate, another is the isopentenyl pyrophosphate. Very simple reaction, head to tail SN2 reaction. Okay. So, from this geranyl pyrophosphate, again look at geranyl pyrophosphate, this is a very good leaving group because this is again allylic to the double bond. So, another isopentenyl pyrophosphate by a similar mechanism can displace this. And if that happens, what you will get? You will get this compound. This will be now C15 containing compound. So, this is what is called farnesyl pyrophosphate. This is a sesquiterpene. By the way, the monoterpenes, if you strip off the pyrophosphate, you will get what will be called geraniol. Then geraniol can have different isomers where the double bond changes position. They are called citral, and you know citral, citronellal, they are the constituents of the home that disinfectant phenyl that will get the white color, the doctor's phenyl. That is basically the smell that we get is out of citronellal, okay. Or it could be the aldehyde form also, the CHO, but these are all very good perfumes. They are used as perfumes, geraniol and citral, all this, and citronellal. Okay. They are actually differing from the position of the double bond. Now, now you know how that the C15 unit is obtained. It is basically 3 isoprene units are doing SN2 substitution. So, now the task is that to join this C15 unit into another C15 unit. Okay. So, this is what is that? We have done that. Okay. The next. Now, this farnesyl pyrophosphate and another farnesyl pyrophosphate, they combine with each other. Okay. Let us go back to this one. What is the second reaction? Second reaction also is between, this is the head and this is the tail. It is a head tail combination, right. Head tail combination. Now, when the two farnesyl pyrophosphates combine, there is a problem. Problem means the mechanism is not that very simple, it is actually very complicated mechanism, but here the two heads are combining with each other. Okay. If time permits, I will give you the mechanism. Two heads combine with each other. How that was proved? Because they used labeled carbon here and labeled carbon here, and they found that the labels are actually this carbon carbon bond. So, now without going into the mechanism, you can do just join this carbon with that carbon. How the reaction is taking place, I will give you some idea. But anyway, this is very important, the two farnesyl units are attaching by head to head combination, and this is what is called squalene, that is the C30 unit. Okay. Squalene is the C30 unit, and let me come back to this mechanism. I will discuss a little bit, because after all this is organic chemistry. So, we have to show what is this mechanism, but before that we many of the books are actually writing wrong things. So, I am not showing that. I later realized that what I am copying is not correct. So, I will show you in a very simple manner, but now the same squalene you can write in a different fashion. It is the same squalene. Squalene is nothing but your this long chain, but it can fold into this fashion. Okay. And now, what happens? The squalene forms an epoxide here. This is called squalene epoxide, 2,3 epoxide, okay, because that is the 2,3 carbon, okay, 2,3 epoxide. Now, what will happen? You see, it is a very interesting reaction. So many reactions. Today we talk about cascade reactions, domino reactions, all these things, but nature's domino reaction you see one after another. First, in presence of an acid, enzymatic acid, say BH plus, that protonates this epoxide. Epoxides are susceptible to acid catalyzed ring opening. So, it will open definitely from this side, because that cation is stabilized. So, now this is going to attack here. So, you form the first 6 ring, then this is going to attack here, you form the second ring, because this cation, when this double bond moves, it forms a cation here. So, then that double bond attacks here, it is a cascade reaction, that forms a plus here, this attacks here, that forms a plus here, and now this attacks here, that forms the completes the 5-membered ring. So, this is the first sterol that you get. Okay. This is called lanosterol. Very interesting reaction, and many people tried to have made different synthetic strategies doing domino reaction or a cascade type of reactions. Okay. So many carbon-carbon bonds are formed in a single reaction, and everything is also the other point to remember is that stereochemistry is also only of one type. This methyl is beta, and this methyl is also beta. This so the stereochemistry is all maintained. It is an extraordinary reaction, the formation of lanosterol from squalene epoxide. And then we are not going into the details, then this is ultimately converted into cholesterol. Okay. Then this is converted into cholesterol. So, two things now, the one thing is remaining, that how this squalene is formed. Now, if you remember the structure of farnesyl pyrophosphate, it is here. Do not look at this, we just try to copy this, not this one, before that. Yeah. The farnesyl pyrophosphate, we will not write the entire chain, we will write double bond and then OPP and put R here. Okay. And then it is a reaction between the head groups. So, another OPP, and then you have a double bond here and a methyl, and this double bond also had a methyl here. Okay. And then R1, say this is R, this is R1. Now, what will happen? It is like an SN1 mechanism. Earlier, so far we have when we added one after another these C5 units, the reaction was by SN2. If it goes by SN1 type, that means this can first SN1 basically you form the cation, and this is also possible because this is a stabilized allyl cation. So, if you form the cation, then what happens? This double bond now will migrate like this, and it forms R double bond, then this double bond, then a. So, we will make this a little bit a circle, bold circle to know the different carbons. Different colors will be better. Let us see whether I can get different colors. So, this is red. And then, so what I am getting up to this point, I am getting, I have come up to here, that is the black carbon, the dotted, and then you have what? You have a connection between the red and this one. So, then you have no, sorry, not the red, this is actually attacking in this fashion. I am sorry, little bit, just a second, this might give a wrong impression. This is attacking in this fashion, okay, because that carbocation will be more stabilized. So, you get a connection between this, suppose I put this also black. So, that is a black, and then you have CH3, but this is a positive carbon, then R, and at this carbon you have a CH2 OPP, OPP. Okay. But remember the ultimate, let us see, the ultimate connection should be between this and that, but that we have not done yet. This plus, then what happens? A hydrogen from here is lost, making an anion here, and that attacks this carbon. So, now it is all red, let us see, that is fine, the double bond, the methyl, and then you have a what is called a cyclopropane. You will have a cyclopropane now. Sorry, cyclopropane, yes, that is okay. Cyclopropane, we have to be very careful about the these carbons, where are these desired carbons. So, this is the black carbon attached to, this was the red carbon, by the way, this was the red carbon, this was the red carbon, that means the black carbon is, and this is the black carbon, sorry, this is red carbon and this is the black carbon. and then you have this CH2OPP, and this black carbon is attached to R and a methyl. Okay. Now, what will happen is a rearrangement reaction. This is red. This is red. Okay. So, this is the cyclopropane. Now, this rearranges that bond. I will tell you what happens here. There is a, so that comes here, the phosphate goes out. So, that if that comes here, this goes out, okay. And then you have a cyclopropane here. So, you generate what, a positive charge here, there is a hydrogen, there is no hydrogen here. So, this is a positive charge, and that will be neutralized by a double bond. So, let us now discuss this head to head combination of farnesyl pyrophosphate to squalene. Okay. The mechanism is, up till now we have seen that this carbon carbon bond forming reactions go via the SN2 type displacement, but this head to head combination cannot have that. What happens here is, basically this is the R group is that long chain, and this R group is also long chain. They are same, basically virtually they are same compounds. Okay. In one of the arm, the pyrophosphate leaves, so generating a cation here which is stabilized by the double bond, allylic double bond, and then there is this double bond which moves, generating a carbocation at this center, tertiary center, and that forms a carbon carbon bond. So, basically what happens, if this is a this is the carbon and these are red carbons, and suppose this is a red carbon. So, what happens, you have this is as red, this is as red, and this is as red. Remember, what you want to do ultimately is the formation of, see, these are the black carbons, a black red combination. Okay. So, now after this, seeing that positive charge, a hydrogen will lose from here, and that forms that anion forms the, quenches the carbocation and forms a cyclopropane ring. Okay. So, basically what happens, where is the black carbon? This is the black carbon, and this is the your red carbon, this cyclopropane. Okay. These are all red. Now, what happens, this there is a rearrangement of the cyclopropane that comes to this direction, kicking out this phosphate, pyrophosphate, basically pyrophosphate. So, you get a new, so what you get is a new cyclopropane. Where are these the red and the black ones? I think this is the black one which is marked red here. So, this is the, sorry, this is your cyclopropane. Where is your black carbon? Because you have to have a, so this is now that carbon carbon bond formation has taken place, but in the process you have again created a positive charge here. So, now this one, this bond migrates, this is cyclopropyl methyl cation. This is a very well known reaction, that if you have cyclopropyl methyl cation, a rearrangement which is called Demjanov rearrangement, that this is lost. Okay. Homoallylic cation is generated. So, basically what you do, you double bond, then you have these two connections, then you have a double bond, you have a methyl, you have a R, but you have a positive charge somewhere. That positive charge is where? Oh, not the double bond, you have a positive charge here, on the red one. On the red one you have a positive charge. Okay. On the black one is neutral, because the bond has been broken in this fashion. So, red is positive. Now, what happens, there is a Na, this enzyme is NADH or NADPH dependent enzyme. So, that acts as a reducing agent and delivers a hydride here. So, that is how this this bond formation has taken place. This is black, this is red. Fairly complicated. Just have a quick summary, very quick summary, that the first, this head-head combination. So, one pyrophosphate leaves generating a cation, the double bond attacks the cation, then a hydrogen is lost forming a cyclopropane, then there is a rearrangement of the cyclopropane generating again a cation here, and it is a cyclopropyl methyl cation. So, that will definitely open up to form a homoallylic cation, and that homoallylic cation, homoallylic on this side, okay, homoallylic cation, which will be reduced by NADPH, and that is how the two squalene are combined. Okay. And I already told you that what happens here, that that forms squalene epoxide, and the cascade reaction gives you the first steroid, that is lanosterol, and that is processed, and ultimately cholesterol is formed. Now, all these are so many steps. Now, how to stop the biosynthesis of cholesterol or modulate? What has been found, that out of all these steps, scientists have found that the rate limiting step of this biosynthesis is the formation of mevalonate from HMG CoA. Where is that mevalonate from? So, that is in the very beginning. You have this here. So, you have this HMG CoA, and there is an enzyme called HMG CoA reductase that forms the R malonate. So, the rate limiting step is S HMG CoA is reduced to R HMG CoA, R mevalonate is going into R mevalonate by the enzyme which is called HMG CoA reductase, by the enzyme which is called HMG CoA reductase. Okay. So, what you need is a reversible inhibitor of HMG CoA reductase. Okay. Fortunately, nature has provided us these compounds. We have not, nature always comes to the rescue of mankind, and what we found, that this is the compound. These are collectively called statins, and you will be surprised to know that these statins are the largest selling drugs in the world, statins. They work remarkably well, and see, before you have the hypertension already set in your body, you can always control the cholesterol by starting taking the statin. Okay. And there are several statins now available, but remember, these are natural products, and then there may be some semi-synthetic. Semi-synthetic means you take the natural product, changes some places by synthetic methods. Okay. If you look at the statin has this type of bicyclic decalin type system, and you have this lactone, hydroxy delta lactone. Okay. The question is why it will act as a reversible inhibitor. If you open this lactone by hydrolysis, what will happen? It will have CO2 minus OH. Okay. And on this side you have this substituted ring pattern, whatever is there, complicated. If you take HMG CoA as the substrate, going into what? Going into the mevalonate. This is HMG CoA, which is SCOA. Remember, CoA is a very large molecule. So, this CoA part is being mimicked by this substituted ring, but the other component is so similar. You see this carbon, then you have this tetrahedral position, and you have this CH2 CO minus. So, basically that is the mimic. This mimics the HMG CoA, as simple as that. Okay. So, all these statins work by that principle, and they are extremely good, they are reversible in nature, and there are different compounds now available, lovastatin, rosuvastatin. See, once first generation compounds come, then the second generation, third generation comes. Okay. But remember, these are the largest selling drug in the world today, because it is a lifestyle disease. Thank you. So, this is all about the cholesterol, this cholesterol biosynthesis, and how to stop that hypercholesterolemia. Okay, that means high cholesterol content. Okay. So, that ends up, I think, all the, see, still there are many drugs which have not been covered, I know, but in this course, the bridged course, we have tried to cover as many topics as possible, which are extremely important, which are of daily use. So, I think we tried to give you a glimpse of the development of drugs, and you see everywhere there is organic chemistry. Talk about any antibacterial compounds, their mechanism of action, beta lactamase reaction, and then how to make molecules which are beta lactamase inhibitors. You talk about neurotransmitters, you talk about angiotensin converting enzyme inhibitor, everything is ultimately, it comes down to writing the molecules, try to see what is the nature of the active site, and then try to have the interaction studied. But it is basically the flow of electronic and steric nature, steric factor in organic chemistry that goes into the biology. So, this is the end of it, but what we will do, we will take few extra classes, and that is where we again revisit the courses and discuss the problems that are some problems work out as which will clarify the doubts that we have in the process of delivering these lectures. Thank you.